decided to reteach an abstract of the whole course during the online classes. Okay? All course material will be taught again in English. An abstract of the course. I prepare a new set of the slides. These slides are abstract versions of the slides in the درس‌ها. Where is Muhammad Ali? Ziauddin, can you translate to Arabic? Hi Ziauddin. Ziauddin.
Yes, doctor. Good evening.
How are you?
Alhamdulillah.
Thank you very much for your cooperation in translating the slides in Arabic.
In your service.
Okay, thank you.
Doctor, you see 22% was voted about the English. That means we have 22 one understand you.
Yes, but someone says that like Asra,
Yeah.
it seems Asra
الأستاذ
is
يقول اخوان الأستاذ يقول
women.
أنا راح أشرح المواد كلها بالإنجليزي، راح أعيد ترجمتها، كل المواد راح أعيد تدريسها بالإنجليزي. أوكي، وراح
I'm here. Ziauddin. It seems that Ziauddin is offline. Okay. Do you have one voice? We continue on English. I hope you can understand carefully. After each online class, I send you a set of homework. These homework are from the content given in that session. Your grading is based off these homeworks. The first item is your homeworks related to your online classes. Second item of your grading is computer assignment. We have some computer assignment on OpenMP. We have several computer assignment from the SIMD section that I will be deleted them for this semester. Okay? Therefore, your final grade have two parts. First, your homework. Second, your computer assignment using OpenMP language. Plus a final exam. Final exam is based off the material reviewed by you in these two items, in homeworks and in OpenMP codes. Okay? If you have any question, please ask now. Okay. At the end of this session, I will say you about the OpenMP and its prerequisites. Do you have my sound? Okay. It's my mistake. Sorry. With Linux, you can simply set up OpenMP and you can simply use it. But in Windows, you may have some difficulties. Linux is a bit better, but if you don't have Linux, we can use Windows. Prepare a computer for next 2 weeks. I think I can provide you the computer assignments from next 2 weeks, and you can use your computer to solve the assignments. Okay. Let's start the course from the very beginning. If you don't have other questions, I'm going to start the course from sequential computer. Any C or C++ compiler. In Linux, you simply could use GCC or G++. But in Windows, you should use the heavy Visual Studio or MinGW. MinGW is the GCC equivalent in Windows environment. Okay. As we said in previous session, a sequential computer is a computer that used to solve a problem. To solve a problem, we should divide the problem to many instructions. And our computer executes instructions sequentially, one after another. This is a traditional approach. But modern application require faster processing, which means this computer should faster execute this instruction and this instruction and this instruction. We call this approach uniprocessing. To faster processing, in the first level, we can use faster uniprocessor. As we said in previous lecture, fast uniprocessors in two levels can be made. In two levels, we can be made faster uniprocessors. First, circuit level. We reduce the size of the building blocks of the CPU, called transistor. If a processor of about 10 years ago had this size, a transistor in a modern processor has this size. Shrinking the size of the transistors leads us to higher frequency and faster processing. It is clear. My language is clear to you? Okay, thank you. This is a very good approach, but have a big problem that called power wall. If we reduce the size, frequency increases, and therefore the power will be increased. This is the main problem. Increasing the power due to reducing the size of the transistors. Now, in modern processors, on such a small footprint, a processor dissipates about 150 watts. 150 watts on such a small footprint. We cannot cool the processor with common fan. It's a main problem. Reducing the size is good for faster processing, but is terrible for power. All of you have problem with my voice? Okay, so I continue. This is the first problem. Power wall. Due to the power wall, we cannot increase the frequency as we expect before. Therefore, it stops increasing the frequency. The second problem, the second approach to achieve a faster uniprocessor is done in microarchitecture level. It is a topic that requires a deep understanding of computer architecture. Here, I just mention a high-level view of this topic. In microarchitecture level, we try to execute instruction together. It means that in this figure, what's the microphone? Habib? In ILP, instruction level parallelism, we try to execute this instruction in parallel using a uniprocessor. It's a semi-complicated theory, but it can be done using the advanced microarchitecture. But this approach also have some problems that we can call it ILP wall. Okay. As a conclusion, to build a faster uniprocessor, we can attack to this problem in two levels. First, circuit levels. Second, microarchitecture level. In both levels, we have some problems. The first Powerwall and the second is ILP bar. Moreover, assume that we increase the frequency of the processor. We build a very fast uniprocessor. Okay? Assume that we have a very fast uniprocessor. But a processor requires a memory to store and read data. A processor writes to the memory and read from the memory. If we have very, very fast uniprocessor, we require a very fast memory. Unfortunately, as you see in this diagram, a processor's performance increase faster than the memory performance. Therefore, in 2005, in this year, we have such a gap between the performance of memory and processors. A big gap. Okay, if I try to increase the performance of the processors, I will increase this gap that acts as a wall to increase the overall performance of the combination of processor and memory, which is called computer. Therefore, after 2005, increasing the performance of uniprocessors have been stopped. But a big question, how we can do faster processing? The alternate solution is parallel processing. Do you have any question? Jawad Kazem. Due to the increasing the performance of the memory, this gap reduces every year. Which part, Hebe? faster uniprocessor or circuit level? Okay. A short repeat for heaven. We have a traditional uniprocessor. I want to increase its performance, to do faster processing. How we can do it? How we can do faster processing using a uniprocessor? First, in circuit level, we can reduce the size of transistor. But this have a major problem called power wall. Therefore, shrinking transistors, power wall. Therefore, we cannot continue this approach forever. Okay? Could you understand? Ebe? The second one, microarchitecture level. You do not require deep understanding of this section, this part. In microarchitecture level, there are mechanisms such as ILP or pipelining that help us to increase the performance of a uniprocessor. But it has some problems. This problem called ILP wall. First problem, power wall. Second problem, ILP wall. No. Power wall means that the temperature of the CPU is greater than that can be cooled by traditional fans. Okay? The problem of the power wall is the problem of temperature. Second is ILP wall. Okay, thank you, Jawad Kazem. And the final problem is memory wall. What was memory wall? I said you that a processor performance raises faster than the memory performance. Therefore, a gap created between the performance of processor and memory. Therefore, processor should wait to read from memory, or write to the memory. Should be wait. This wait reduces the overall performance. Okay, we have a traditional uniprocessor. I try to increase its performance with circuit level approach or with microarchitecture level approach. We face three major problems. First, power wall, second, ILP wall, and the last, memory wall. And the silver bullet is parallel processing. This alternate approach helps us to reach higher performance without these three problems. Okay. What is parallel processing? In parallel processing, instead of having just one processor, we have several processors. And we split the problem in several parts, and then we execute each part 1, part 2, part 3, and part 4 as a uniprocessor and execute these parts of a uniprocessor. In this problem, we split the problem into 4 parts and execute them in parallel. Okay. In the next few slides, I'm going to talk about the parallel computing platforms. Wait a minute, please. Ask me, Jawad. This gap exists. This gap exists. We cannot fill these gaps. We should wait for the scientist who works on the semiconductor industry to invent a new memory that acts as fast as processors. We just, in architecture level, use multiple processors to read from memory and write to memory simultaneously. Okay? Okay, this gap is a minimum gap. Cache L1, L2, L3, or any levels of cache could reduce these gaps. But this gap presented in this figure is the minimum gap, including cache. You mentioned a topic called memory hierarchy. Memory hierarchy. Yes, cache could reduce the gaps, but cannot fill it. Okay. We can see the parallel computing platforms. Thank you too. From two different views. First, logical organization, and next, physical organization. Assume we have a parallel system with many processor elements or processing element, processing element, processing element, processing element, processing element. This box is a parallel system with 4 processing elements. PE stands for processing elements. Okay, a parallel system with 4 processing elements. From the logical organization point of view, which is the programmer's view of the platform, we face with these 2 issues. First, control structure of parallel platforms. Allahu Akbar. What do you say, Muhammad Jafar? The PDF of these slides. I will upload these slides, this series of slides, after the class. درسا, yes. On درسا. Okay, you can find each slide on the main slides, but this series is abstract. The parallel computing is created to prevent the processor from sluggish operation. I will upload this slide, this PowerPoint on the درسا. Don't worry. Okay. In this slide, I'm going to say that all parallel computing platforms, we can see from two different views. First, logical organization, and second, physical organization. In logical organization, which refers to a programmer's view of the platform, we face with two issues: control structure and communication model. And in physical organization, which refers to the actual hardware organization of the platform, we have two other issues: architecture of the computer, architecture of the parallel computer, and interconnection network for parallel computer. In the next 4 slides, I'm going to talk about A, B, C, and D issues. Okay, control structure of parallel platforms, Line taxonomy. A program is just a combination of instructions and data. A program is a combination of instruction and data. In fact, a program is nothing but instruction and data. Instruction, data. Data, instruction. Or in discretized form, we have several packets of data and several instructions one after another. Instruction and data will enter the processor, will enter to the inputs of the processor. Okay, here. But there are 4 different states. We can enter into the processor one instruction and multiple data. Instruction, data. In first state, single instruction and multiple data we can enter to the processor. Next, we can enter to the processor multiple instruction, multiple data. Next, I can enter to the processor one instruction, one data, or single instruction, single data. بله زیادین.
Excuse me. Okay, this is in the first lecture,
Okay.
the introduction
You're welcome.
that you explain now. I said that
I can't hear you.
this is
Repeat again.
subjects that you explain now in the introduction.
Okay. Yes. I explained this subject in the
Yeah, I know.
introduction, and you translate it to Arabic.
Where is it? About the SID, MID. I thought that it is in the third lecture that I translated. Yeah. In the third lecture.
Yeah.
Right? Because I want if we reach to the subject of this is season 1 or season 2, if we arrived. Okay.
Wait a minute. I see the slides. I think
this is not in that introduction.
yes,
Season 3? Season 3?
There are in lecture
3, 4, 5. Okay. Before that subject, I have a question. I want to to ask about the conventional uniprocessor, about the diagram for single cycle implementation and the steps of which the instruction and read registers and execute ALU, memory read, write registers. That's
yes. Ziauddin, you can ask about the pipeline or single cycle implementations in WhatsApp because I delete this content for the course, and these abstracts are the main content we have mentioned in this course. I think that subjects are too complicated for many of the students.
Okay, if we deleted that, you mean you deleted it? Okay, for the new lecture.
Yes. Okay, but I'm in your service in WhatsApp.
For
you can
the
ask
new
your
lecture.
question. I will answer you.
The new lecture we have deleted from it many subjects of it. Okay, that's you mean, Doctor? Thank you. Okay.
Yes.
Thank you.
Yes, exactly. Thank you very much. Okay, and the final state is to enter multiple instruction and single data. Multiple instruction and single data. This is called SIMD. This is called MIMD. This is called SISD, and the latest called MISD. Flyn's taxonomy. SISD, MISD, SIMD, and MIMD. As you see, the SISD, where just one instruction and one data bit at the input of the processor is same as uniprocessing. One instruction, one data. MISD, which means multiple instruction with just one data, is impractical. We do not have any computer with this architecture. We do not have any computer with MISD architecture. SISD is traditional computer. MISD is impractical. SIMD SIMD, single instruction, multiple data, is available in our course in SIMD sections. All Intel processors support this state. Single instruction, multiple data. It's very, very, very useful for graphical tasks for image processing. Single instruction, multiple data. But it is a type of parallelism. We process several data. For example, in this figure, 4 data at the same time. It is a type of parallel processing. But in MIMD, we have another approach. In MIMD, we have another approach. We enter to the inputs of the processor several instructions and several data. Each instruction can use its related data. In this course, we will learn how to program the systems with SIMD architecture, and also we will learn how to program the systems with MIMD architecture. A quick look at the الجلسة. Session 5, Session 6, Session 7, and Session 7 and Session 8 are for SIMD sections, and the good news, these sessions are optional. Session 9, 10, 11, and other sessions are about OpenMP that supports the MIMD programming. Okay. This is the control structure of parallel platforms we mentioned here in section A. In B, we mentioned the communication model of parallel platforms. What is the meaning of this name, communication model? We have in a parallel system several processing elements. These processing elements, as I mentioned here, work on a same problem. Same problem distributes between these processing elements, and these processing elements try solve the problem together. Therefore, sometimes they need to communicate with each other to exchange the results. For example, these processing elements generate results that is required by this processing element. Therefore, this processing element, this PE, should send its result to the next processing element. Okay? Therefore, we require a communication media, how this processing element talk to each other, how this processing element talk to each other. Any question? Okay. Thank you very much. There is two major methods. Method first and second method. First method, shared memory. What is the shared memory? What is a shared memory? A big memory, just a big memory, a single big memory, used by all of processing elements. These processing elements read to and write from this memory. This processing element, this and this processing element, all read and write to and from this memory with shared between them. We call this shared memory. How this shared memory help the processing element to communicate with each other? It's simple. How? These processing elements write the results in a location in memory. This processing element writes its results to a shared memory, a location in shared memory. Each processing element, if we call this processing element 1, this 2, this 3, and this 4, if another processing element, 2 or 3 or 4, wants to read the results of the first processing element, just should read this location. Okay? Therefore, processing elements can communicate with each other through a shared memory device. Okay. These two subtopics will be discussed in the next slides. But what is message passing? What is message passing? In message passing, we have a processing element with its dedicated memory here. We have a processing element with its dedicated memory here. We have a processing element with its dedicated memory here, and so on. This could be my computer in my office. This could be the computer of Ziauddin, is his home. This could be the computer of Hebe, Ziauddin, Kabe. This could be the computer of Ghufran. When I compute a results, send the results to the Ziauddin, if Ziauddin requires that, through the internet. All of our computers are connected together using the internet. If the Ziauddin computes a result that Ghufran needs it, send it through the internet to the Ziauddin, to the Ghufran. As you see, this is a bit complicated in comparison with the shared memory. But fortunately, this method is less common nowadays. Okay. In this course, we focused on shared memory. But what about uniform memory access and non-uniform memory access? UMA on NUMA. Yes, send and receive instructions. We have library for do that called, for example, MPI, Message Passing Interface, introduced by Intel. Okay. But for shared memory, as we know, and one of your friends mentioned it, each computer have a processor or processing element and have a memory. But to reduce the gap between the processor and memory in performance, we add cache here. Cache acts as an interface between the memory and the processor. Usually, we do not have a big memory. We have many small memory, like this figure. Therefore, we have many processing elements and we have many memory. How we can connect this processing element to this memory? The first method. We place the memories and processing element on the ports of an interconnection network. If each of processors wants to access to one of the memory, do it through the interconnection network. For example, this processor can simply read from or write to this memory using the interconnection network. It does not matter. Does not matter for the interconnection network that which processor send a request to access to which memory. Okay. This is an important point. I will repeat. It does not matter for the interconnection network that which processor send a request to access which memory. Okay? Access time for all of memories, this memory access time to this memory, and this memory is equal for this processor and this processor and this processor. It means that this structure is uniform. All access times to the memories are equal. As you see in this figure, we don't have cache. A better implementation of this uniform memory access shared memory is the one we placed a small cache next to processing element. We can assume that this part, and this part, a processing element plus its related cache, such as a processing element in figure A. Therefore, this structure is still uniform. It means that this processing element for access to this memory requires a time same as this processing element to access this memory. T1 and T2. T1 is relatively equal to T2. T1 is relatively equal to T2. Allahu Akbar. Please translate. Rest? No rest. We should cover the topics in 3 or 4 sessions online. Okay, thank you. But we have two: uniform shared memory and a non-uniform. In non-uniform, we move the memory from the right side. We move the memory from the right side to the left side next to the processor. We call this model non-uniform because this processor requires less time to access its memory, we call T8, in comparison the time required to access the memory of another processor, T2. T8, T1 is smaller than T2. Okay. This lecture will be recorded. I think we will finish this lecture until 4 o'clock. Okay. Therefore, we call this architecture non-uniform, and the two first architecture uniform. All about the access time to the memories. Do you have any question? It does not matter if it is better or worse. It depends on the application. For some applications, non-uniform is better. For some application, uniform is better. No sound? Do you have my voice? One, two, three. Yes, you can see this part like a traditional computer. or traditional processor. But you can see that the whole system is based on communicating them with each other. Okay. No problem. Thank you, Ziauddin. 7, 8, 9. Okay. A, B, and C, all of figures are about the communicating between processing. بله محمد علی، کجا بودی محمد علی؟ بهت نیاز داشتیم نبودی. کل محتوا مفصلتر از این خلاصه ها به صورت آفلاین وجود داره. محمد علی اگر هستی، من برای اینکه مطمئن بشم بچه‌ها صحبت منو فهمیدن، میتونی میکروفونتو وصل کنی، یعنی درخواست بدی میکروفون بهت بدم یه بار دیگه صحبت‌ها رو براشون بگی. خب محمد علی هستی؟
بله دکتر هستم.
کجا رفته بودی نبودی اول کار؟ محمد علی؟
جانم دکتر جانم، صداتون دارم.
خب من صدای شما رو ندارم و قاعدتا بچه‌ها هم قطع و وصل میشه صدات، یعنی اینکه اگه الان صدات استوار هست من بگم. اول اینکه شما کجای ایرانی یا عراقی؟ عراقی؟
جونم.
محمد علی؟ عراقی شما؟ خیلی عالی. من میگم جمله به جمله، لطفا شما برای بچه‌ها، اصلا کلش رو بهت میگم برای بچه‌ها بگو. نگاه کنید، محتوا به فارسیه، محتوایی که توی سایت گذاشته شده. کل درسی که من برای بچه‌های ایرانی تدریس میکنم به فارسی توی سایت قرار داره.
خب
اما چون برای بچه‌های عراقی زبان فارسی درکش دشواره، من اومدم خلاصه از اونها رو تو همین، چون کلاس‌ها آنلاینمون 4-5 تا که بیشتر نیست، خلاصه از اونها رو تو کلاس‌های آنلاین به انگلیسی دست و پا شکسته میگم که بالاخره مقداریش رو بچه‌ها متوجه بشن. پس این خلاصه گفتن ما، یعنی چیزی که تو کلاس آنلاین میگم خلاصه همونها، سعی میکنم به انگلیسی بگم که بچه‌ها بهره ببرن.
اینه که الان دادین درسته؟
تا اینجاشو میخوای بگو تا بعد من. آره اینایی که الان دادم و جلسه قبل گفتم. و ارزشیابی من و نمره دادن من هم بر اساس همین چیزهاست.
شباب يقول ملخص هذا اللي انطاهني بهاي المحاضرة والمحاضرة اللي قبل، ملخص هذا كلهم موجود كفيديو عندكم منزله.
این هم بهشون گفتید که من از همینایی که تو کلاس آنلاین میگم تمرین میدم و امتحان میگیرم.
خب
گفتی محمد علی متوجه نشدم.
چونه؟ الو دکتر صدامو داری؟ بچه ها میگن هومورکی که بهشون میدی منظورتون چیه؟
به نظرم شما صدا رو درست نداری. درست میگم؟
هومورک یا مثلا
محمد علی میخوای یه کاری کنیم؟ فکر میکنم اینترنت شما خیلی اینترنت خوبی نیست. اگر میخوای لطف کنید توی واتساپ به من پیام بدید، من بدونم شما کدوم یکی از دوستان هستید، بعد همونجا باهاتون بیشتر صحبت کنم راجع به کاری که توی درس میخوام بکنم که بچه‌ها بتونید منتقل کنید.
بله.
تو گروه کلاس هستید که شما؟ آره متشکرم. بعد یه پیام اونجا اگه به من بدی ممنون میشم، اونجوری کمترم چیز میشه، وقت شما رو اینجوری تو کلاس میگیرم. دست شما در منتظر پس پیامت هستم اون طرف. مرسی ازت محمد علی. Okay. I will continue the course. With the physical organization of parallel platforms. Back to the top topic. We talk about the logical organization, Line taxonomy, and communication model, shared address space, and message passing. Now, I'm going to talk about physical organization. In physical organization, first, we should talk about random access machine. Random access machine is not but the computer we talk about there. A traditional computer. A computer with a processor and a memory. Nothing but this. A processor plus a memory. But it works in another way. The random access machine, from the high-level point of view, is a traditional computer with a processor and a memory, but in details it works different. We do not require to know its working algorithm. A uniprocessor random access machine is a uniprocessor, a processor with a memory. But how we can build multiprocessor using this machine? How we can build multiprocessor or parallel processor using this machine? Three approaches exist. 1, 2, and 3. PRAM, LMM, and MMM. In a PRAM, as we said before in shared memory, we place all processing elements next to each other and a shared memory for all of them. We talked about this in previous slides. In local memory machine, we called it parallel random machine or PRAM. In local memory machine, LMM, we place the processor and memory and its dedicated memory next to each other, and then connect them together using an interconnection network. We call this machine local memory. Why? Because we have local memory. This local memory makes this machine non-uniform memory access. And modular memory machine, we place processor and memory on different ports of an interconnection network. You can make a 1-to-1 correspondence between PRAM, LLM, and MMM, PRAM, LMM, and MMM with the figure stated in this slide. This slide and this slide. Okay. And finally, in this session, we should talk about the interconnection network. A black box presented here. What is an interconnection network? Interconnection network is a mechanism for data transfer between processing nodes. For example, this dark node is a processing element. Processing element could place in a topology like this, or in a topology like this, or a topology like this. Each topology has pros and cons. For example, if node A wants to talk to node B, in this topology should send data to this node, then this node, then this node, and finally this node. 4 links between node A and node B. In this topology, A to reach B should be trace for links. But this topology, in this last topology, A just require two links to reach the node B. In this topology, A could talk to B from two different paths, yellow path and red path. But in this topology, we have very more paths. Two paths, at least four paths. Okay. Which topology is better or which topology is worse? We should talk about the metrics used to comparison the topologies. The metrics are stated here: node degree, regularity, symmetry, hop count, distance, and diameter. We talk about these topologies in next session. No. Random access memory is another thing. This is random access machine. Okay. This lecture is recorded. No, I think a medium speed computer is sufficient for download the content. Each session is less than 50 megabytes. Okay. Please don't forget to install Linux or provide a computer for your computer assignment. In session 8, as you see, we add some videos to teach you about the installing the softwares required in SIMD section. This portion of the lecture is optional. Yes, Amir Muhammad. Okay, if you don't have any question, we can finish the class. Could you send me the link of the topic you mentioned in WhatsApp? I cannot understand what you say. Rosha, Jawad, Kazem. Rosha? Rasha. You have my number. If you have in WhatsApp group, you should have my number. I try to repeat the necessary part of the course in English in online class. In this class, next and next and next classes, I'm going to teach in English. And these sessions will be uploaded on Darsa. Yes, yes. Yes, Sebe, you can ask me in WhatsApp. اوکی. خدا نگهدار بچه‌ها. مراقب خودتون باشید. انشالله تا جلسه بعد. خداحافظ شما. Be more active in WhatsApp. Goodbye.